Hello, let's talk about robots. Or let's talk about where we are today with robotics and what is still really far away. And you might know this from the Lord of the Ring that everything that is gold does not glitter. Everyone, those who wander are not lost. Similarly, in robots, we have every robot that dances cannot necessarily handle the manipulation. There's a company called Neura in Germany. They make pretty good robots, and they launched this advertisement recently. It's about the cleaning robot. So this is a family which wakes up and does like a whole mess when they're having a breakfast. They spill things around, they scatter around toys, which is like a normal family. Ta-da, yeah, here goes the orange juice. And they leave a house in a very messy state. And once they go out, a robot comes out and cleans up everything, tidies up everything. So when they're back, they find this very immaculate house. Um, so yeah, so they come back to a very nice and clean and homely house. Now that's a dream for everyone to have. Dr. Jim Fan from NVIDIA talks about it as the physical Turing test for the robots. But we're nowhere close to it. Like we're nowhere close to this kind of robots. Like we still have a way to go. Or you might have seen the dancing robot from Tesla. And like when my friends see it, they think like, okay, if the robots can dance, it could like very easily water the plants, tidy up the room, make you a cup of coffee. But it cannot. Like we still have some way to go. That's what I meant. Like every robot that dances doesn't necessarily handle the manipulation. It's not necessarily a generalized robot. You have to like really understand it. And the best way to do is to show you like where we are right now when it comes to robotics. Like what can the robots do consistently and which are not just part of demos or advertisements or media hypes. So let's take a few examples, and I'm gonna miss like a lot of good examples. So maybe you can tell me more about it. But I'm just gonna talk for now, like a few main examples. Like one of them, when you talk about foundational robotics models, I think Gemini is probably like a good example, other than like GROOT or everyone else is they have a pretty good generalized models, so which can pick and place and make a different box for you, put the pain away, like in this case. So yeah, it's tidy up, but it is still, like I said, like a good demo. They show like it generalizes in a decent way. So this is what a robot can do, and this is not the minimum. Like this is not the base. This is like the maximum accuracy for robots where we are right now. Like this is the best that what robots can do. Now, if you talk about generalization, there was this really nice demo from physical intelligence people where they took robots and they dropped them in like 10, 20, I forgot, like homes that were not unseen and booked on the Airbnb in the kitchens. And they did like simple tasks. Put up in the dishwasher. I think fix me a breakfast was one of them where it was more like putting things on the plate, like prep the breakfast. And this is like a really good demo for generalization. So if we can drop a robot in a unseen Airbnb home and it can do things for you, so understand the shrunk, the cupboard, and take things out of it, understand where the kitchen is, put stuff in the kitchen. That's already pretty good stuff. And like I said, this is where we are. Like this is state of art. This is not the base. This is the top level for what robots can do. Now you can see everywhere, like the tasks are not more than 5 to 10 minutes long. So you cannot leave the home and let them clean up your house. And basically, and then when it comes to like the performance over a long-term task, one of the nice researchers from a company called Dyna, where they demoed this robot which does a task of folding the napkins. Once again, this is a simple task according to human, folding the napkin, but the robot can do it for 24/7 without any kind of policy drift, that is without making any mistakes and with high accuracy. And a robot doing a napkin folding for 24 hours without making a mistake is a state of art, right? So once again, this is where we are, which is very impressive. Don't get me wrong, but we're not anywhere close to robots that will clean our apartment over the weekend or that will take over the world on a next Thursday morning. Right? When you see a media article, think about it again, please. Now, we're doing this course to basically bring you up to the speed to what is state of art in robotics today. Now, this material is part of the in-person course that I'm doing at the university here in Berlin. And we plan to develop this material and most likely will redraft everything and launch it hopefully by fall of 2025, say in September or October, let's say. Now, what has changed? Like, why is now a good time to to get into robots? Like, where we are and where are we going? Now, this is like a really nice example for why we haven't had yet the robots that can clean your house on the weekend or that can just clean after you. Why don't we have the robot butlers yet? Uh, this is where we have been stuck so far. So robots can very narrowly follow like a specific trajectory. They are very expensive. They are very expensive because they have to be so good that they should not have even like a 0.1 millimeter of error in following like a small trajectory. Now, this is a good example because you can see like it's following the same trajectory. It is caged, so it is not interacting with humans. You don't necessarily see. I mean, I'm pretty sure there's a camera somewhere, but it doesn't look like a visual control feedback robot. So what happens is that until now we had robots where they were very accurate to follow the same path again and again and used in manufacturing. And because they had to have this accuracy, they were very expensive for the hardware tolerance that they had to have. Now, if you compare this to humans, like close your eyes, try to move a cup from point A to point B, and try to do it again like 10 different times. You won't be able to do it exactly with millimeter accuracy because you have the feedback coming from your sensors, like from your eyes, basically. And this is what the intelligence is about. This is what the current AI robotics is about, giving intelligence or giving this sensory feedback to the robotic hardware so it can do things on the fly. Now it started with uh, it started with in 2012 with AlexNet and deep learning, where we started solving computer vision, basically understanding the scene, task, objects, classifications, and everything around it. We built on top of it using reinforcement learning, for example. I think you guys remember this project from OpenAI, solving Rubik's Cube. It was done completely in sim, doing a lot of domain randomization in the physics in physics, using a lot of domain randomization with the rules of physics at the same time with the visual component to it. And they did RL to figure it out. So that's so we evolved, like we got quite far away with the RL, also thanks to GPUs, like which is I think one of the main rocket fuel, what's pushing everything. Um, then there's something called imitation learning where you basically learn from like it's supervised. You can think of it as a supervised learning. And there's like old lecture from the great Andrej Karpathy, not lecture, the Tesla autonomy day, I think it was, where he talks about how Tesla does it inside the company. It's a pretty good one. You should check it out. Um, then right now we are in the stage of world models, vision models. So we are at the LLMs, right? Like large language models and vision language models, where we are training the robots or combining the current state of art vision language models to bring that kind of intelligence to the robots, like what Gemini is doing. It is basically Gemini 2.0. So Gemini Robotics paper was talks about Gemini 2.0 being fine-tuned with embedded reasoning with robot data, which can handle like a lot of ego perspective tasks from the robots. And so we have that. Then we also are seeing like first robotic foundational models, like Gemini Robotics or like Pi 0, Pi 0.5 or GROOT. Now, these models are still small when you talk about a large model, like compared to the current state of our LLMs or VLMs, the robotic foundation models are tiny. When I can imagine there is a future where we have there's a future where we have a giant robotics model, but which still follows like a low latency because depending upon the task, it can take the shortcuts, like like the right pathways, and if it needs like a more compute or for the more complicated task, it can select like more complicated pathways. Like it can learn to take like shortcuts. Also, like it's similar to big LLMs where in the training they learn to generate a lot of these short circuits, like the short pathways to to yeah for some of the tasks at the later stage of training. So I think robotics might follow the same policy where you have longer pathways for complicated tasks and shorter connections for like daily tasks. So you can actually have like one big robotics model comparable to the current LLMs and VLMs, which might run locally or even on the cloud, but has the latency of like 250 compared to the humans. Um, then we have thing we'll very likely see world models coming to the robotics, and now I'm pretty much believer in the world models because since I read the paper from David and Schmidhuber. Um, Now the idea of world model is that so we humans, we have a one model for everything. For example, if I throw a ball at you, you're gonna catch it. Like the reason you do it because you can predict the future, like how the trajectory of ball will move, and you kind of because our visual system is not necessarily that fast. It's like it also takes like something around 200 milliseconds for us to for the whole pathway, but we're still much faster, like once because of the world models, and you need those, I think, in robotics too, because if without that, no matter how good the policy is, we are always like 1 or 2 frames behind real-time scenarios. So having world models which are grounded in physics uh, as the base for the robotics foundation models could could lead to all the generalized breakthroughs in robotics. Once again, like just my own speculations. Now, this is all the talks about the policies and training. So different models we talked about. We talked about different training ideologies, imitation learning, reinforcement learning. Um, then you also have the data side. So like basically, how do you collect the data? You have the daily operation. There are a lot of big teams and very smart people working on synthetic data set and simulations. For example, DreamGen from NVIDIA they talk about generating new videos, so they call it neural trajectories, and then using those as the training data. They also discuss the ratio being 10 is to 9, 1 is to 9 or 1 is to 99 as the co-training recipe. Then you also have people like Rosy diffusion model who are using the diffusion models for distractions, for creating distractions in the scenes and those. Yeah. Then it's about learning from the human demonstrations. So I think Tesla had a pretty good demo recently where they showed like the current task that Optimus is learning is basically they have figured out how to learn from ego demonstrations. So like we have this whole spectrum of the data that we also can use and should use for training robotics. Obviously, the holy grail is if the robots can learn from YouTube videos. Yeah, and I think Google will figure it out if they haven't. Or because they have, I mean, I said Google not because not because anyone has no chance, but it's because they have the access to YouTube. Um, Now, similar to the general LLMs or everything that we see in deep learning, machine learning, or AI, the robotics would also be the company that has the biggest data sets or can collect like most diverse and varied data set will be one of the best people to solve robotics, as you're seeing in the self-driving cars, like Tesla has probably the biggest data set on imitation learning and also one of the most diverse data sets thanks to people buying Teslas and the shadow learning happening inside it. Similarly, Waymo and Coma AI are probably next one in the quality and quantity of the data sets, which makes them, and as you can see, like they have probably the best models or best technology right now when it comes to self-driving. And we should see the same thing in robotics. Now, to get started, you don't need a very expensive humanoid or a self-driving car. You can start with something very simple like a robotic arm. So Hugging Face did something like built a Lay robot And I cannot imagine anything that is simpler or easier for anyone to help you get started with robotics. You can buy the robotic arm or you can build one yourself. If you want to buy it, you can buy it from Wow Robo, or there are like few other manufacturers and partners from Hugging Face who are selling the robots. Or you can build one yourself, assemble it, follow the guide from Hugging Face, the layer robot example. It's very, very well written. It's very hard to make a mistake if you're following the guide and not get your first train policy. So assemble the robot, or if you buy already assembled robot and configure them. If you buy already assembled robot, calibrate the robot. Once you have calibrated it, check out the teleoperation for the robot. It's like I said, it's as simple as just copy pasting it. Copy the script, paste it in your terminal, and you basically get to do it. So once you have tested the teleoperation, collect your first data set, record your first few episodes. So when you're doing your first few episodes, remember, like, try something simple. Just do a pick and place, for example. If you're doing pick and place, keep the place location fixed and do the pick, like vary the pick location maybe 2 or 3 times for say 50. If you're collecting 50 episodes, maybe choose like only 2 or 3 diverse location to do pick and place, and try to keep the grasping style constant. Once you have that, train the ACT policy and deploy it. So that should give you, like, that should warm you up to using the robot framework. That should warm you up to general the idea of robotics and the imitation learning we're doing here. And once you have that, you can jump on to the next lesson, which is building agentic robotic arm using foundational models. So we're imitating, we're reproducing Gemini Robotics using Gemini and Pi0. And there we will then walk through the details of doing it and building a generalized robotic arm. Now, the tech and everything that we're building is not limited to the arm, right? Like you can take the same technology and deploy it for the cars, for the humanoids, or even for the defense robots or drones. It's up to you how you, like, once you learn about it, like how you where you bring your what application do you apply it to. All right, guys. All right, everyone. So lesson 2 is already online. Everything is still a draft. We have to polish it up, but it's already online. Hope you have fun. And ping me if you have any questions, or there are going to be a lot of mistakes. So when you find one and you have an idea how to improve it, let me know about it. Thank you.